Hello, Sauce here. I'm going to write down a sequence of numbers you might have seen before. 1, 1, 2, 3, 5, 8, 13. I'm going to continue for a little while. 21, 34, 55, 89, 144, and this pattern continues. This is a sequence. It's an ordered set of numbers. It's the Fibonacci sequence. It's very famous. Let's talk a little bit more about the sequence of numbers. We know that when we have a sequence, we can use notation t sub n to stand for the value of the nth term of the sequence. And because a sequence is ordered, it has a particular set order, we use n to stand for the position or any position in that sequence, where the initial position is 0. It might be initial position of 1 in some books and resources, but there are many reasons, especially for computer science, where we want to think of sequences in series starting with a position number of 0. And our position numbers increase from there and continue to go on forever, just like the Fibonacci sequence. How is the Fibonacci sequence generated? We have a recursive formula for it. It cannot be found explicitly. A recursive formula requires knowing the values of a previous term. In this case, 2 previous terms have to be found before we can find a next term. So this formula is t sub n, we could call this the value of the current term, is based on the sum of the 2 previous. The notation for the value of the term 2 previous to n is t sub n minus 2. And the notation for the term previous to term number n is t sub n minus 1. This here, again, is the recursive formula for finding the values of the Fibonacci sequence. Add the 2 previous. We can check it. 1 plus 1 is 2. We can check that 13 is the sum of the 2 previous 5 and 8. The Fibonacci sequence comes up in study in science and aesthetics, patterns in nature. Let's take a little deeper look at the Fibonacci sequence by making ratios out of sequential terms. 2 terms that are sequential means that they are next to each other in the list. If I make a ratio of a value of a term divided by the one previous, then a pattern will emerge. What that means is that if I think of this term number, this term value 1, and I make a ratio of it divided by the value of the term previous, then these 2 sequential terms make the ratio 1 over 1, and I can make the decimal equivalent of 1 over 1 is, of course, 1. I'm going to continue to make a sequence out of these ratios in fraction form very quickly. That is the term value 2 divided by the previous 1, and I can keep going. This is simple enough to do, and of course, this forms a sequence of ratios that are based on Fibonacci numbers. And this sequence of ratios also keeps going forever. Let's analyze the decimal equivalents. I've got them in fraction form, but if I do the division 2 divided by 1, I get 2. 3 divided by 2 is elementary enough. It's 1.5 or 1.5. And then it gets a little more sophisticated after that, but I'm going to continue And I'm going to round the decimal approximations when I need to the nearest thousandth. I'm also jogging them because I need some space to write them down. And I'm checking. I'm going to leave off this. This would be the next one. I've got use of space. I want to point to the corresponding fractions. Let's take a look at this sequence of decimals. The sequence starts at 1, quickly jumps up to 2, and then back down and up a little more, down a little more. So we're going up and down. It's not continually rising or continuously decreasing. It's going back and forth and converging upon this decimal 1.618 that I can see is repeated in the last two ratios. This number, 1.618, is very special. I'm going to write a more expanded form of this number, a more complete approximation, 1.61803398875. This number is what we call the golden ratio. It's a ratio because it came from observing a sequence of ratios. Students might be familiar that the golden ratio comes up in a geometric study of a nautilus shell, which is a sea creature. And I'll remind you that that nautilus shell, geometrically, can be thought of as inside of what we call a golden rectangle. Golden rectangle is a rectangle that uses the golden ratio number in its dimensions. If we write one dimension as 1, then a golden rectangle is going to have the proportion where the longer dimension is the golden ratio. This is an irrational number. It keeps on going, of course, but I've approximated it to the nearest thousandth. So that nautilus shell, many people might be familiar, if you've seen a poster or a drawing, is partitioning the golden rectangle and drawing an arc of the sea creature's shell, and we continue to partition it with the golden ratio proportions. And if we continue and draw the shell within our partitions, this pattern repeats and it gets infinitely small, and the nautilus shell curls in this very particular manner. This is an example of the golden ratio coming up in the patterns of nature. And the nautilus shell is not the only way. There are countless ways that we can find this number expressing itself in nature and aesthetics and music and art. One more thing to say, this ratio was created by taking a term value in the Fibonacci sequence and dividing by the one previous. If we form a ratio where we take a term value and divide by the one ahead of it, which is the reciprocal of the study that we made here, then we will get a very similar number. It will also be the golden ratio, except that it doesn't start with the leading 1. It's less than 1. But these two ratios are reciprocals of one another, and they both generate the golden number.